Hi, my name is Gibran Sandoval, and on behalf of my research team composed by Dr. Elvia Sanchez, the Dr. Ventaka Krishna Kartik, and chemical engineering student Julia Astudillo Avila, I will be presenting this research project Enhanced Gas Sensing using zinc tungsten with carbon quantum dots nanocomposites, the synthesis, characterization, and performance evaluation. Now, trace detection of environmental pollutants is crucial for human health and various technological applications. Metal oxide gas sensors have gained attention due to their low cost and simplicity. Despite their high operating temperatures and humidity sensitivity, these sensors have remained viable. To address these limitations, different composite materials have been used, such as platinum with zinc tungsten or zinc oxide hybrids. Recently, carbon quantum dots emerged as promising materials to their different functional groups on their surfaces, demonstrated by the study released by CU for nitrogen monoxide detection using zinc oxide carbon quantum dots. In this study, zinc tungsten carbon quantum dots composites were synthesized and characterized for gas sensing applications. The methodology followed is a combination of two reported synthesis methods. In one hand, we have the zinc tungsten reported by Shiley Young that consists in a co-precipitation technique of sodium tungstate and zinc nitrate in a 1:1 molar ratio. By the other hand, we have a slightly modified carbon quantum dot synthesis reported by Jayakumar A, where lemon peel is dried, grinded, and dissolved for its use in a hydrothermal synthesis. The obtained solution is centrifuged and filtered, so only a carbon quantum dot solution remains with no other organic matter. For the sensor preparation, both the zinc tungstate and the carbon quantum dots were mixed in an ethylene glycol solution at around 40 degrees Celsius. Once the solution looked homogeneous, using a pipette, 5 layers were deposited in the glass substrate. The same procedure was followed for pure zinc tungstate and carbon quantum dot sensors. For the gas sensing test, we use a homemade device designed by the Dr. Venkatakrishna Kartik. The device consists of a heating chamber where our sensor is placed on top of a heating resistance and two cables that conduct electricity. The resistance keeps up the sensor up until the material enters its semiconductor state. The two cables measure its conductivity and resistance in order to determine the ideal conductivity point. Once this temperature is reached for the gas in the gas sensing part, a valve is opened and introduces our testing gas, in this case acetone. The electron exchange between the gas and our sensor creates a difference in resistance that can be measured in certain patterns. These patterns can give us multiple information about the nature of our sensor. Now, talking about our results, let's start with the carbon quantum dots fluorescence spectroscopy. This was done in order to determine the presence of carbon quantum dots and not just any kind of organic matter. We can see the peak intensity at the 430 nanometers emission wavelength and 350 nanometers excitation wavelength. This is consistent with results found on literature. Now, we can physically see this behavior in the photos presented at UV light for both the carbon quantum dots and the composite, emitting a blue light. Now, about the structure of zinc tungstate, carbon quantum dots, and our composite, we measure an X-ray diffraction pattern, the FTIR spectra, and Raman spectroscopy for the three powders. However, carbon quantum dots measurements not only for the X-ray diffraction but also for Raman and the gas sensing applications were faulty due to the high hydroscopicity of the carbon quantum dots. So they are not presented here due to being very faulty and very misleading the spectras. In X-ray diffraction, when comparing the maximum peaks of the zinc tungsten patterns with the composite ones, we can see that both spectra basically don't share almost any relevant peaks in the same angle. This may be due to the amorphous organic matter present in the composite, thanks to the carbon quantum dots. Now, this is difficult to identify the corresponding zinc tungsten peaks in the composite. However, it's reasonable to assume that the crystalline structure was modified and there was a displacement of the peaks. Towards if it's towards left or right, we cannot determine it yet. But this indicates that it's an maybe different crystalline structure and not just a physical nature. Now, similar conclusions can be drawn from the Raman spectra, as the main tungsten with oxygen peaks seems displaced and or partitioned into other smaller peaks in the composite spectrum. About the chemical composition of the carbon quantum dots, we can see in both the FTIR and the Raman spectroscopy many carbon and oxygen bonds, having a strong presence of carbonyl groups in both, possibly from acid groups that we can see in the FTIR spectra. We can also see many carbon double bond peaks, mainly in the aromatic region. In the FTIR spectra, we can see a narrow proliferation of carbon and hydrogen, indicating the possibility of the presence of graphene in the carbon quantum dots. In sum, with the presence of acid and carbonyl groups, we could reasonably assume the presence of not only carbon quantum dots, but maybe also graphene oxide quantum dots. However, further testing is needed to confirm this theory. Now, going into the acetone sensing characterizations, we can see an improvement between the pure zinc tungsten sensor and the composite one at higher concentrations, mainly starting at 4 parts per million. The sensing and recovery response shows an improvement at higher concentrations of 1 and zero point 0.6 megaohms per second, respectively. The recovery percent also seems to have improved at higher concentrations, mainly around 10 parts per million, and is far greater than any recovery percentage present in the zinc tungsten at even lower concentrations. Now, why does this happen? We suspect it has to do with the carbonyl and acid groups present in the carbon quantum dot surface, being the ones responsible for the charge exchange with the acetone. However, further testing and DFTD simulations will be required to confirm this theory. In conclusion, the zinc tungsten and carbon quantum dot synthesis in this study shows a structural, chemical, and optical evidence of the carbon quantum dots incorporation in the zinc tungsten structure. Carbonyl and acid groups possibly played an important role in improving the acetone sensing capabilities in higher concentrations. However, FDTD binding energy simulations are needed to corroborate this theory. Further carbon quantum dots characterization is also needed in order to correlate their structure with the present composites, and for future carbon quantum dots application in other senses of or their role in interacting with other gases. To close this presentation, I would like to thank Julia Studio for her help in this project, as well as the Dr. Elia and the Dr. Kartik for their help in making this project possible. We also would like to acknowledge Dr. Edilso for their collaboration in the conduction of the X-ray diffraction analysis, which was fundamental to determine the properties of our composite. Without further to say, that would be everything from my part. Thank you.